This is the first lecture of Chapter 14, which deals with alcohols, ethers, and thiols. We'll first concentrate, however, on alcohols. In this presentation, as I mentioned, we'll concentrate on alcohols. So first we'll look at the chemical structure of alcohols. How do we identify alcohols? Next we look at the classifications of alcohols. As you can imagine, there are literally thousands of different alcohols of organic chemistry. So we can classify them into different groups so we can appropriately study them. Next, we'll look at the nomenclature. You may recall we have the IUPAC, International Union of Pure and Applied Chemists. They established a set of rules so that scientists throughout the world will have a consistent way of communicating the names of organic compounds. Next, we'll look at the properties of alcohols. Remember, the properties here are observable or measurable characteristics of a compound. And lastly, we'll look at reactions of alcohols. Of course, being a course in organic chemistry, we cannot escape the reactions that are possible for these different molecules. Let us concentrate now on alcohols. What is an alcohol? An alcohol is an organic molecule that has the OH functional group. Remember, organic chemistry is the study of compounds that are mainly composed of carbons and hydrogens. There are some heteroatoms, different from carbons and hydrogens. Oxygen is a heteroatom, so this is a molecule or set of compounds that have a heteroatom, and the functional group is the OH. So this OH is bonded to a carbon of the hydrocarbon or the organic compound. Here is methanol. As you know, that's a fuel. And this OH is bonded to this carbon. If you draw out the lowest dot structure, you'll see it's CH, H, and OH. So this is the more condensed way of writing this molecule methanol. Here's ethanol, another organic solvent. This OH is bonded to this carbon. Here's isopropanol, also known as rubbing alcohol. As you can see here, this is the line angle representation, where this is a CH3, a CH, a CH3, and the OH is bonded to this CH. Here is ethylene glycol, which is a diol because it has 1 and 2 alcohols. Ethylene glycol, of course, as most of you know, it's the main ingredient in antifreeze. And another important compound is propylene glycol, which is also a diol, 2 alcohols. So these are examples of alcohols, and they can be identified by the OH functionality. As I mentioned, there are literally thousands of different alcohols. So to study these many alcohols, we can classify them into groups. So one classification of alcohols is based on the carbon that the OH group is bonded to. So here's the OH, here's a carbon that is bonded to. If this carbon has 3 hydrogens, as this one has, it is described as methanol, or a methyl alcohol. This one here is a little different because here's a carbon that this OH is bonded to, but it's bonded to 1 carbon containing alkyl group 1. So this alcohol is described as a primary alcohol, usually written as 1 superscript, because it's bonded to one alkyl group. That could be a CH3 or some other alkyl group. Look at this one. This OH is bonded to this carbon, and this carbon is bonded to 1 and 2 other alkyl groups or carbon containing groups. Since there are 2, this alcohol or this type alcohol is described as a secondary alcohol. So again, a classification of alcohol. Of course, the third possibility is if this carbon is bonded to 1, 2, and 3 different R groups or carbon containing groups, it's a tertiary alcohol. So you should be able to classify alcohols based on the number of alkyl groups that are bonded to the carbon that contains the OH group. We'll have some examples at the end of this section. But let's move now into the IUPAC nomenclature of alcohols. So here's an alcohol. Once you have identified it as an alcohol, start numbering at the end closest to the OH functionality. You will see why in a moment we number, because we need a root name. So we can start over here. As you can see, this is 1, 2, 3, and this is 4 for this carbon that has the OH. If you start at this end, this is 1, 2, and 3. This is 3 for this carbon that has the OH. So this is the correct numbering in this direction. Why number? Because we utilize the number of carbons to determine the root name. The longest chain that has the OH group will dictate the name of that molecule. This molecule has 6 carbons. So it has its root name is hexane. Remember, we had to memorize that chart or have it available. So that's the starting point. We changed the E of the hexane to OL. So the name becomes alkanol. In this case, hexanol. We will have to indicate the location of the OH group, which is on carbon number 3, so it becomes 3-hexanol. Make sure you write the OL so it's legible and we can read it. Here's another example. Again, we start numbering here and not here because this OH is closest to this end of the molecule. 1, 2, 3, 4, 5, 6. That would be hexane. The E goes to OL, so it's an hexanol. And of course, the OH group is on carbon number 2, and that 2 goes here. So the name of this molecule is 2-hexanol. Let's look at branched alkanes. You may recall when we're looking at branched hydrocarbons, we start numbering at the end closest to the branch. In this case, however, we start numbering at the end closest to the OH. So here again is our OH group, and here's our branch. We could start numbering here, but that's incorrect. The IUPAC's rule states that we have to start numbering at the end closest to the OH, so we start here at number 1. So again, why we have to know these rules is because the chemists in Europe and in various parts of the world, they will communicate names of molecules, and based on these rules, we know the structures. So we go 1, 2, 3, 4, 5, 6, and that becomes a hexane, as you will see here. So it's a hexane. The E goes to OL, as you'll see here. We'll have to indicate the position of the OL or the OH group, which is a 3, and we'll have to indicate the position of the methyl, which is on carbon number 5. So this becomes the IUPAC name of this molecule. Here's another example. Start numbering at this end and not at this end because of the OH being closer to this end. The methyl group, there's a branch. This is a methyl group. Remember, this is the line angle. So each line represents here a carbon which has 4 bonds to it. So this is a 2-hexanol and 4-methyl. Here's the methyl right here. So that is the IUPAC name of that molecule. You should also be comfortable if given the name of a molecule, can you come up with the structure? So you should be able to work forwards and backwards in terms of name to structure and structure to name. Let us look now at cyclic alcohols. This one is fairly simple because you identify the number of carbons in the ring and just add cyclo to the name that we had before, so it becomes cycloalkanol. Of course, the AA alkanol here just means the alkane or the corresponding alkane. So let's look at this molecule. This one has 1, 2, 3, 4, and 5 carbons, and it's in a ring, so therefore it's a cyclopentanol because of the OH. Because 5 means, the term for 5 is pentane, so it becomes pentanol. Here's another one. 1, 2, 3, 4, 5, and 6, so it becomes hexanol, and since it's a ring, it becomes cyclohexanol, and of course it's not surprising that this is cycloheptanol because of 7 carbons in the ring. Let's look at branched alkanol. Excuse me. Branched cycloalkanol. So here we have to use some numbers, and we need a starting point because it's a ring. So if it's a ring, start at the carbon that has the OH group. That gets number 1. Then you have a choice. You can number in this direction or that direction. You number in the direction of the branch. Number in the direction of the branch. So in this case, you go in this and not this way. So this is the correct numbering. So this is incorrect, of course. So this becomes the correct numbering. So this is 1, 2, 3. So 3,3-dichloro. And of course cyclohexanol. You need not put the 1, but if you put the 1, that is not a wrong answer, but it's just understood to be 1. Here are some examples that's in your book. Here's ethanol. You need not put 1 because it's understood to be 1. 1-propanol. 1, 2, 3. This is propyl alcohol, a common name for that molecule. This 1 is important because it could be 2-propanol. So this is 1, 2, and 3. And of course the OH is on carbon number 2. So we use 2-propanol. 1-butanol, 1, 2, 3, and 4. 4 is butane, so it becomes butanol. Same here. And let's look at this one. This is 1, 2, and 3. Propanol. 1-propanol, because here's the 1. And 2 for the methyl group. Here's another one. Notice we're not going to start here because this is not a ring, so we start 1, 2, 3. So this becomes a branch. So it's propanol, 2-propanol, because OH is on carbon number 2, and 2-methyl because this methyl group here is also on carbon number 2. And of course this is cyclohexanol. Here's a common name, tert-butanol. It's a common solvent in organic chemistry, but the IUPAC name is right here. And this is a common name. Okay, so let's do a quick little test here to see how well we have understood these concepts and if we can apply these concepts to solving problems. So give the IUPAC name for these molecules. So first of all, they're alcohols because here's the OH, and we'll have to start numbering from one end. So we know we start numbering from the end closest to the OH. Here's a cyclic structure. Here's an alcohol, so this will be number 1. But notice here the stereochemistry. Wedge and dash. Don't forget this is a CH3 because we're using the line angle. Here's another one. Again, we start numbering from this end because the OH is closest to that end. So just start numbering, and based on the number of carbons that are present, you will derive the name. Here's another one. OH is here, so this is number 1, 2, and 3. So we have 2 methyl groups bonded to number 2. So now we have to apply our knowledge of IUPAC nomenclature of alcohols to naming these molecules. Let's see what we get. This one is pentanols, 1, 2, 3, 4, 5. And the OH is on number 2, and there's a methyl here. Notice the trans, because we have here a trans arrangement of these 2 groups. One is up and one is down. And of course, start here for number 1 because we're naming it as an alcohol. So this is 1, 2, 3, 4, 5, 6 cyclohexanol, 2-methyl because of that 2. We start at this end for this molecule, 1, 2, 3, 4, 5, 6, 7, heptanol, and this 2 indicates the position of the OH. Here's the last one. We start here, 1, 2, 3, and of course that's propanol, and 1 indicates the position of the OH, 2 methyl groups, 2,2-dimethyl, because these 2 methyl groups are on carbon number 2. Here's a test of our understanding of the classification of alcohols. So the question now is to classify each of these as methyl, primary, secondary, or tertiary alcohols. So again, before you answer that question, you'll have to make sure you understand what's being asked. It's classification. And remember, classification here means the carbon that has the OH. We look at what is bonded to it. If there are 3 alkyl groups, then it's a tertiary. 2 alkyl groups, secondary. So again, identify the OH functional group. Let's look at this one, for example. This is a carbon that has the OH. So the question now is, how many carbon groups are bonded to this carbon? Don't forget, since we're using the line angle, here is a hydrogen here, because there are 4 bonds to a carbon. So right away you can see how many alkyl groups are bonded to this carbon. So let's look at the answer. So this is a methyl because this carbon here has no alkyl groups, just 3 hydrogens bonded to it. This is secondary because this carbon has 1, 2 alkyl groups bonded to it. Of course, the 4th is a hydrogen. so therefore it's a secondary. This is a primary because this OH is bonded to this carbon, which has just one alkyl group. Here's a secondary. Don't forget, here's a hydrogen that's not shown. So here's 1 and 2 alkyl groups bonded to it. So that's a secondary. This one is a secondary again because it has 1 and 2 alkyl groups. Of course, the other one is a hydrogen. So that's a secondary. It's a tertiary. Here's a carbon. It's bonded to 1, 2, and 3 carbons. So it's a tertiary alcohol. As I mentioned, this is important in organic chemistry because we have literally thousands of different alcohols. So if we can put them into categories or groups, we can better study and understand their properties and reactivity. Let us turn our attention now to the physical properties. As we mentioned, physical properties are properties of a molecule or characteristics of a molecule or molecules that are observable and measurable, such as the color, and measurable such as the boiling point. Those are all properties of molecules. But to determine the properties of molecules, we need to determine if they are polar or non-polar. Alcohols are polar molecules. Why are they polar? Because we have a carbon that's bonded to an oxygen. You will recall that oxygen is more electronegative than carbon. So look at your periodic table and you'll see that oxygen is to the right of carbon. It's closer to fluorine, which is the most electronegative atom. So therefore this bond here is a polar covalent bond, which means that these 2 electrons here are closer to the oxygen than the carbon. So the symbol that's used is delta negative because it pulls the electrons towards itself. If it's pulling the electrons towards itself, that means that this carbon here is partial positive, as indicated with this delta positive. Here's another covalent bond to oxygen because oxygen takes 2 bonds. As you know, hydrogen is very electropositive. So these 2 electrons here in this covalent bond are closer to the oxygen than to the hydrogen. So therefore this is again delta negative and this hydrogen is delta positive. Whenever you have polar covalent bonds in a molecule, that molecule is described as a polar molecule, especially if the geometry is like this. So, conclusion, alcohols are polar molecules. Let's see the consequence of the polarity. The consequence here is that in the liquid state, alcohols are associated by hydrogen bondings. Remember, hydrogen bonding here is a hydrogen. This, of course, is hydrogen. And this is oxygen. A very electronegative oxygen. If it's close to a very electropositive hydrogen, we can have a attraction. And this intermolecular attraction, or attraction between 2 molecules, it's called a hydrogen bonding because of the hydrogen that's involved. So you can see here that alcohols are involved in hydrogen bonding to each other, intermolecular hydrogen bonding. As a result, the boiling points of alcohols are higher than non-polar molecules with similar molecular weight. So to have this liquid boil, you'd have to supply enough energy to break these hydrogen bonds so that the individual molecule can escape into the vapor phase. That requires energy. That's why you have to heat this liquid to a higher temperature to break these bonds, to get these molecules into the individual molecules into the vapor phase. For nonpolar molecules, where these intermolecular attractions don't exist or not as strong, they have a lower boiling point. So let's do the comparison. So you can see here, methanol and ethane, they have about the same molecular weight, but look at the boiling point, 65 degrees for methanol and minus 89. It's a gas at room temperature for the boiling point. So the same applies for just one more, ethanol, boiling point of 78. Propane, which has a similar molecular weight, is minus 42, much less boiling point. It's a gas at room temperature because, again, of the intermolecular hydrogen bonding that exists between these molecules. So energy must be supplied to break them, to have it boil. Therefore, it requires more heat and a higher boiling point. Solubility. Polar molecules are soluble in polar solvents. So here's an example of antifreeze. As I mentioned earlier, antifreeze is actually ethylene glycol, which is CHOH and CH2OH. So that's ethylene glycol. As you can see, it's polar because of the OHs here, so it's very soluble in water. So the solubility of alcohols are pretty much the same as that of water, depending, of course, if it's a very small alcohol such as methanol or ethanol. Now let's concentrate on reactions. So the type reactions that alcohols undergo, one very important type is called the elimination reaction. As the name implies, it's the removal of water, which is H and OH from, here's the key, adjacent carbon atoms. From adjacent carbon atoms to form alkenes. So let's go over that again just to make sure we get it. Alcohols undergo elimination reaction. As the name implies, elimination means removal. It's the removal of water or H and OH from adjacent carbon atoms, and the product that's formed is an alkene. So let's look at this molecule, cyclohexanol. Here's the OH, and here's an H on the adjacent carbon. So this carbon has the OH. Here's the adjacent or the next carbon over. It has a hydrogen in the presence of an acid as a catalyst and heat. This is heat here, the symbol for heat. It produces water. Here's water, H2O, and an alkene. So here's another example. Here's the alcohol. On adjacent carbon, there's a hydrogen, so we can have H2O coming off as water, and a double bond forms here. Okay, you may ask, is it possible to have the same thing over here? And yes, it is. What you'll get is that, and I hope you recognize that these two molecules are the same. So either one is a correct answer. So, as a summary for that, and then we'll look at some more examples. Elimination is the removal of water to form an alkene. It does not automatically happen. It has to be in the presence of an acid, strong acid, as you can see here, phosphoric acid or sulfuric acid, pretty strong, 85%. Another aspect is This reaction occurs much faster if, or much slower, I should say, if the alcohol is primary, and much faster if the alcohol is tertiary. So remember, we classified alcohols as primary, secondary, or tertiary. If you have a tertiary alcohol and you're looking at dehydration reaction, that reaction is much faster or easier to occur than a primary alcohol. Let's look at some examples here. So here is ethanol. As you can see, this is a primary alcohol. Notice here the acid is needed, but look at the temperature, 180 degrees C. It gives the alkene, ethylene, and of course water. Let's look at this one. This is a secondary alcohol, and of course here's the hydrogen. So the double bond will form right here. As you can see, here it is, and here's water, but now the temperature is less, 140 degrees, and this is a secondary alcohol. This is a tertiary alcohol. Why? Because the carbon that has the OH group is bonded to 1, 2, and 3 alkyl groups. In the presence of an acid and heat, this time it's only 50 degrees. We get water coming off, elimination of water, and the double bond. So again, alcohols that are tertiary react faster, more favorable, require lower temperature for elimination compared to a primary, which reacts much slower and need a much higher temperature for the elimination of water. Let's look at this here. Here's 2-butanol. Here's the carbon that has the OH. But on the adjacent carbon are 3 hydrogens. And on the other adjacent carbon are 2 hydrogens. So we can form a double bond either here or here. So there are 2 possible products. The question now is, which is the major product? As you can see here, here are the 2 possible products. So we take off this OH and one of these hydrogens, we get this alkene right here. If we take off this OH and one of these hydrogens, we get this alkene right here, 1-butene. It turns out that this is 80%. If you do the percent yield, a lot more of this molecule than this molecule after the reaction is done. You can predict this because the alkene that's formed as the major product has more alkyl groups bonded to the carbons of the double bond. So let's look at this one. This carbon here of the double bond has 1 alkyl group shown in red. This carbon, the other carbon of the double bond, has 1 alkyl group shown in red. So it has 2 alkyl groups bonded to the carbons of the double bond. Let's analyze this one. This carbon of the double bond has no alkyl group because it has just 2 hydrogens. This carbon of the double bond has 1 alkyl group here, just 1, so therefore this one has more alkyl groups bonded to the carbons of the double bond compared to this one, therefore this is the major product. Let's make sure you understand. So let's do another example. Here's the OH, here's the carbon of the alcohol, here's the adjacent carbon, so the double bond can be formed here or here. And here's the double bond if it's here. And here's the double bond if it's formed here. So 2 possible products. This is also good to get you thinking, to Make sure you're observant, make sure you're analytical in terms of possibilities. So there are two possible products. Which is the major product? The major product has more alkyl groups bonded to the carbons of the double bond. So let's do the analysis. Here's one carbon off the double bond. It has one alkyl group and one hydrogen. But the most important aspect here is alkyl groups. The other carbon off the double bond has one and two alkyl groups. So total of 3 alkyl groups. Bonded to this one. Let's look at this one. Here's one carbon off the double bond, has no alkyl group. Here's the other carbon off the double bond, has one alkyl group here. Just one. So therefore, this is the major product. So you'll get a question, of course, in the quiz and on the exam to predict the major product, the major organic product of these reactions or similar reactions. You'll have to carry out these observations and you'll have to make sure that you apply these observations and these concepts to solving the problem. Let us look at one more here, and this is a cyclic structure. So here's the carbon off the double bond, carbon off the alcohol, pardon me, and here is an adjacent carbon, here's an adjacent carbon, and here's an adjacent carbon. So we can form a double bond here, or here, or here. Of course, these two will be equivalent. So let's look at just forming the double bond here. So here it is. That's one possibility. And forming the double bond here, that's the other possibility. Which is the major product? Here's the carbon off the double bond. One carbon off the double bond. It's bonded to one and two groups, so that's 2. Here's the other carbon off the double bond. It has a hydrogen and bonded to 1, so that makes it 3 groups. Let's look at this one. Here's one carbon off the double bond. It has none. Here's the other carbon off the double bond, 1 and 2, so 2 alkyl groups. Therefore, this is the major product for that reaction. The last one, right here, is just another example. Here's the OH. So we can form a double bond here or here. So if you form the double bond, don't forget there's a hydrogen right here. And of course, there are 2 hydrogens back here. You may want to draw the hydrogens on these line angle structure so you're not confused and you know that there are hydrogens there. So we can form a double bond here, and here it is. And we can form a double bond here, and here it is. Which is the major product? Carbon off the double bond, 1 and 2. Carbon off the double bond, don't forget there's an H here, that's 1, so this is 3. And let's look at this one. This carbon here has H, so just this one, 1. This carbon has H, so this one here just has 1, so 2 groups. Therefore, major product. So again, you should be able to predict the major organic product. Notice this is the inorganic product, water, but this is the major organic product because, of course, as we have defined, organic here means compounds that contain mostly carbons and hydrogens. I think this is the last slide, and yes, it is. So again, continue to study hard and note one of the aspects here of your scientific development is to be able to understand the concepts, and equally important is to apply these concepts to solving different problems. So that's developing and building that aspect of your thinking, your innovative and problem solving skills, which is a good reason why you're doing this course, is to aid your thinking and your problem solving skills. So don't try to memorize your way through this course. It will not help you later on as you as you improve your scientific abilities, but develop your problem solving skills and your ability to use information to solve problems. So continue to study hard and solve these problems, and get ready for our quiz and exams that are coming up, and I'll give you an announcement. Okay?